Hola, ¿cómo está? I'm going to tell you a surprising story about how observations of exploding stars called supernovae revealed to us that the universe is not just expanding, that's something we knew before, but is actually expanding faster and faster. That is, it's accelerating. And this is believed to be caused by a mysterious new component of the universe called dark energy. But before I tell you about the exciting parts of the discovery, let me take a step back a little bit and give you some context for understanding this discovery. When we look out at the universe, it looks like it received a big kick we call the Big Bang. And now the separation between galaxies is growing. The further away a galaxy is from us, the faster it appears to move. You could think of the universe like a giant loaf of raisin bread rising in the oven. Hopefully you like raisins. Whichever raisin or galaxy you sit on, you look at all the other ones around you and they appear to be moving away from you. So this is how we perceive the universe. But you might wonder, how do we really know this? How do we really know that this is the way our universe acts? And the answer is, based on looking at this animation, you need to be able to measure how far away galaxies are and how fast they appear to be moving away from us. In order to accomplish that, astronomers like myself look at distant galaxies and try to gauge their distances. And so we might see a galaxy like this that has 100 billion stars in it. And what we look for is a special object that we call a standard candle. An object whose luminosity we understand well, so we can tell how far away it is from its brightness. Now, one of our favorite standard candles is an exploding star called a supernova. When one of these stars explodes, it can be as bright as a couple of billion times the brightness of our sun. So it might look like this. And of course, the further away it is, the fainter it will appear. That is, the light follows what we call the inverse square law, that the brightness declines as 1 over the distance squared. So if the supernova is twice as far away, it will be 4 times as faint. If it's 3 times as far away, it'll be 9 times as faint. So the brightness of the supernova tells us how far away that galaxy is. But what about the other part? What about that apparent motion of the galaxies in the animation? Well, astronomers can look at the light of a supernova, and we know the wavelengths or color of the light as it's emitted. But a funny thing happens. As that light travels to us in the expanding universe, the wavelengths of light are stretched, and longer wavelength light is redder light. The color becomes redder, and so we call this the redshift. Notice that although it looks like the galaxy or the standard candle has a velocity away from us, it is actually the expansion of space which is causing this stretching and making it look like a distant galaxy is moving away from us. So when we look out in space, we try to find these standard candles. We measure how far away they are. We measure how fast they appear to be rushing away from us. Now I can go back to that animation that I showed you before. Hopefully that'll come up. Oops. Click. There we go. So now we can be more quantitative because astronomers can go out and look for galaxies that host these supernovae. And every time we find one, we make these 2 measurements and we add it to the graph that you see on the side. And the signature of an expanding universe is to see this linear relationship between the two, that the further away a galaxy is, the faster it appears to move. Now, we can measure the slope of that line, and that tells us how fast our universe is expanding today. But if you think about this, it might have occurred to you that when you get to the far end of that line, you are actually looking into the past. It takes light a long time to reach us from distant parts. And so you might expect, you might not be surprised, if the slope of that line actually changes as you go to the past. That is, further back, perhaps the line bends one way or the other, if the universe is speeding up or slowing down in its expansion, and we would have the hope to learn about that. Thinking of this in another way, it's really that we are looking at these supernovae progressively further and further into the history of the universe. So when we see a nearby supernova, that might be telling us how fast the universe was expanding 1 billion years ago, because that supernova may be 1 billion light years away. A more distant one would be perhaps 2 billion years ago. A more distant one, 3 billion years ago. So this is a very powerful way we have to actually measure if the expansion rate of the universe is changing with time. Now, why would you expect the expansion of the universe to change with time? Well, after the Big Bang and everything's moving apart like the animation, then you'll have a configuration of galaxies like this. And although they're moving apart, they have attractive gravity that is pulling on each other. And that wants to slow down the expansion, to kind of slow it down, maybe even bring it to a halt. And so we might expect to see it slowing. However, 100 years ago, Albert Einstein came up with a new theory of gravity called general relativity. And he tried to apply it to the whole universe. He asked astronomers of the day, what is the universe doing? How is it moving? And they told him incorrectly that the universe was static, that it was neither expanding nor contracting. And he puzzled over this because he thought, if the universe was static, then the attractive gravity of the galaxies would make it start to come together. And so it wouldn't remain that way. How does this work exactly? And he made an amazing discovery. He discovered that although the gravity of objects in space is attractive, that the gravity of space itself, of empty space, could be repulsive. And he called this the cosmological constant. Today, we would call this dark energy. So he imagined that the reason the universe was static was that there was a perfect balance set up between the attractive gravity of stuff and the repulsive gravity of space. However, 10 years later, Edwin Hubble and others pointed out to him that the universe is actually expanding, and he thought, I never should have come up with this cosmological constant. And he famously called it one of the biggest blunders he had made in his career. So fast forward to the mid-1990s, and astronomers thought that the universe was either like the picture on the left or the picture on the right. Either the universe, now expanding, was filled with matter, a lot of matter, which would really slow down the expansion. So much so that eventually the universe would stop expanding and then start contracting and would end in a kind of big crunch. That's the opposite of the Big Bang. Or, alternatively, if there was only very little matter in the universe, then sure, it would be decelerating, but not very much, and the universe would expand forever. That is, we would say the universe would have escape velocity from itself. You might be familiar with this concept. You toss a ball in the air, and if you don't throw it with escape velocity, it will fall back down. That's like the universe on the left, because the Earth is very heavy. But if you throw it hard enough, or if the Earth didn't weigh very much, then it would have escape velocity. It would escape. And so this was the question for astronomers in the 1990s. This seemed like a very interesting investigation to try to figure out what the fate of the universe was based on how much its expansion was slowing down. So I told you how we measure distances with supernovae. It turns out there's a very special kind of supernova that really yield the best distances. There's a certain kind of star called a white dwarf star. It's the core left over after a normal star like our sun goes through its life burning energy and running out of energy. The famous Indian astrophysicist Chandrasekhar in the 1930s explained that a star in this state could not exist more massive than 1.4 times the mass of our sun. We call this the Chandrasekhar limit. And so no star can be more than that. However, sometimes a star like that might be orbiting another star. And if these two, while they're orbiting, matter is transferred over, then the star might surpass the Chandrasekhar limit, and that leads to a runaway thermonuclear explosion. It's like a giant nuclear bomb going off in space, always at the same mass. So this makes an outstanding standard candle for astronomers to measure distances, as I described. So by the mid-1990s, my colleagues and I were taking pictures with telescopes of large swaths of the sky that contain tens of thousands of galaxies in every image. And a month later, we'd return to the telescope, and we'd take a second picture. And with computers, we could digitally align them and subtract them and find a new point of light, like you see over there, that would indicate we had found one of these distant supernovae. So within just a couple of years of collecting this information, we were ready to make the measurement and figure out which of those stories I told you was the right one. And the real shock was they were both wrong. The universe was not strongly decelerating. It was not going to recollapse. It was not lightly decelerating. Rather, the universe was doing something quite different. It was actually picking up speed. It is actually accelerating. And although we scratched our heads for a while, the only explanation we could come up with at the time was that that thing that Einstein had suggested, that there could be this repulsive gravity of empty space, that or something like that was going on. In fact, was so important it was actually dominating the attractive gravity that would try to slow down the expansion, so that it looked like the universe had about 70% in the form of this dark energy. So this became the breakthrough surprise, really, of the year in 1998 for Science magazine, that Einstein himself would have been pretty stunned that this idea, this possibility that he came up with actually really existed. Okay, so after a few years of study of this, the physics community has tried to come to terms with what really is going on. What is this dark energy or this repulsive gravity? And we're really not sure, which makes this an incredibly interesting area of study right now, particularly because it touches so many critical areas in parts of physics we don't understand. Our best guess is that it is Einstein's cosmological constant or something like it. In quantum theory, there is always expected to be some amount of energy, even in the vacuum of space, that it turns out that nothing is not really nothing, but really has some energy. And that alone would produce this repulsive gravity. However, there's terrible agreement when we try to calculate how much of this there should be. In fact, it's about 120 orders of magnitude off from the naive calculation. Alternatively, this could be a temporary condition where there's a field in space, like the electric field or the magnetic field. This would be a different field, and it has energy associated with it. And so it temporarily looks like there is this background energy. And the third possibility is that we finally broke in Einstein's theory of gravity. We have never applied it across the whole universe. And so it's possible, less likely, but possible, that what we're seeing are artifacts, really, of not having the right theory of gravity. So the expectation is the next decade, NASA and the European Space Agency are going to be launching dedicated space telescopes, telescopes about the size of the Hubble Space Telescope that will largely focus on answering this question about which of these is correct. And so this should be an exciting decade coming up. So for a little perspective of where we are and where we've come, this is the recipe of the universe, something that was only realized in the last 2 decades. It turns out about 0.05% of the universe is planets, about 0.5% is stars, about 4% is gas or dust. That makes less than 5% of the universe made out of normal matter, the kind of elements in the periodic table of elements that you learn in chemistry class. Everything else, the other 95%, is totally exotic. 25% is in a form of matter, but that's not normal matter. It's likely to be some kind of particle that we have yet to discover in the particle accelerator or laboratory, but we're hopefully getting closer to that. And then there's the 70% dark energy. It is just breathtaking to realize just in the last 10 years or so that most of the universe is in some form that we didn't expect was out there. Just to give you an analogy, the Earth is covered by about the same fraction in water. Imagine that we didn't know anything about water, that we lived inland, and finally we came out to the first lake or beach or shore and said, my gosh, what is this water stuff? We didn't know this was even out there, and we're just coming to terms with trying to understand it. So the next few years should be very exciting. Just to remind you, why is it that we study this dark energy? At this point, it's so central to understanding the universe. It will help us understand the origin and the fate of the universe. It makes up most of the universe, so we can't really say we've even reached the goal of understanding most of the universe. But I think the real reason, the thing that makes it the most exciting, is we have two powerful theories in physics. We have quantum theory that rules over physics at the atomic scale, microscopic. And then we have Einstein's general relativity that rules over large scales, macroscopic scales across the universe. These two theories are not compatible. We've known that for a long time. And so we're always looking for how to unify these. What's so interesting about this dark energy phenomenon is an explanation seems to lie right at the crossroads, right at the nexus of these two theories. So it's our hope that if we continue to follow and see how nature actually does physics at that interface, we might ultimately understand it better. So I'm going to put up a few summaries, and thank you very much for your attention.